Good day, ladies and gentlemen. My name is Chukwuemeka Awah, Department of Electrical and Electronic Engineering, Michael Awah University of Agriculture, Umudike. I wish to present a paper titled Speed and Load Characteristics of Two-Stator Permanent Magnet Machine. The paper ID is 007. The presentation will follow this pattern. 1. We will look at the abstract, then the background of study, we will look at the methodology, then results before the conclusion, of course with some listed references. Yeah, under the abstract, we'll have some points listed here. Number 1, the effect of electric loading and rotor speed on the output characteristics of two-stator PM machine is presented in this paper. Overall, what we looked at is what effect will electric load and the rotor speed of the machine have on the other characteristics of performance, or overall performance of the machine. Then we'll consider the results and saw that the obtained results of the flux linkage and EMFs are both symmetrical and sinusoidal in shape, which is actually ideal for the control of electric machine. Is a desired performance or characteristics rather of a given electric machine. The recorded efficiency of this machine at high operating speed is quite low, almost half, when you compare it with the rated condition or rated efficiency of the machine at the normal operating speed, which is 400 RPM. That's the rated speed. Now we'll look at the average torque of the machine and of course the phase flux linkage of the machine. We saw that it's not affected by the effect of the rotor speed. When you vary the rotor speed, it doesn't affect these two parameters. Overall, in this work, we actually considered the electric load, the effect of the electric load and that of the rotational speed of the machine on the output performance of the machine. 1. We can see the results of the phase flux linkage as against the speed. When we vary the speed of the rotational speed of the rotor or of the machine, we'll find out that it doesn't affect the phase flux linkage of the machine. However, when you vary the currents, if you load the machine at different rated currents, you see that there is this direct proportionality between the currents and the output phase flux linkage or the maximum phase flux linkage of the machine. The higher the current or the input current, the larger the output phase flux linkage. The same thing happens here, or rather a similar thing happens in that of the voltage. When you look at the voltage, the induced voltage of the machine varies directly proportional with the rotational speed. The higher the speed, the higher the obtained induced voltage, as can be seen from the figure here. Of course, we'll look at the FFT of the voltage and presented the same here against the waveforms of the voltage. We'll have some further results. Like we mentioned earlier, the principal or the fundamental cogent torque is that of the sixth order from that equation which we saw in the methodology. And funny enough, the cognitive torque as well doesn't vary with the speed. It's more or less constant as we vary the speed. Hence, it doesn't have that variation with the rotor speed. Also, the average torque doesn't as well vary with speed, as we can see from the graph of average torque against the rotational speed. However, when you load the machine using the Q axis current, you can see we'll see that the PM flux, the flux obtained from the permanent magnets, will more or less remain constant until at about 15 amperes, and at such condition the machine has started experiencing some level of saturation. You see a decline from the normal trend. The efficiency of the machine was also considered. We now found out that at high speed the efficiency is quite low compared to its rated efficiency at the rated speed of 400 rpm. Of course, the obtained loss at that level of high speed is quite significant when you compare it to that of the rated condition. Is the rated condition, under rated condition, the loss is actually insignificant compared to that obtained in high speed, as can be seen from this plot. Yeah, in conclusion, the effect of speed and electric loading on the performance of permanent magnet machine, which has two stators, is presented in this paper. And the obtained total machine loss at normal operating speed is insignificant, as we mentioned before, compared to that in high operating speed. As a result of this, the machine's efficiency at rated operating speed is greater than that in high speed by over 43%. And further, we'll see that the quadrature axis current, that is the Q axis current, which we also know as the magnetizing current of the machine, is noticeably high at there is a noticeable reduction in such variation with flux linkage at high load, and this is as a result of the armature reaction or the saturation effect of the armature windings. Basically, in this work, we looked at how speed and electric load affects the machine performance, or the overall machine performance. That's exactly what we have done in this work. And we'll see that for some parameters, the speed or the rotor speed of the machine doesn't count. However, for most of the machine parameters or the performance of the machine, it is dependent on both the speed and the electric load, the efficiency of the machine at that level of saturation. We'll recommend some future work. One of it is, one, the thermal modeling of the machine could be investigated in order to obtain the temperature effect on the different parts of the machine. And further research could also be carried on the hybrid excitation of the machine, thereby a situation whereby you use both DC and AC sources in order to regulate the fluxes to amenable or to our choice. Also, or furthermore, we can also look at the vibration and noise effect which we can obtain from this machine, and that will also lead to looking at the unbalanced magnetic force which we could obtain from the rotor of this machine, because the unbalanced magnetic force from literature has direct effect with the vibration and noise characteristics of any given electric machine. We've listed some references here, and that's all. Thank you for listening. Thanks.